For podcast 4.2 for chemistry, we're going to talk about how you find the molecular geometry and the bond angle of the Lewis structures that you draw. So you need to make sure you have that table of molecular geometries in front of you. So what you're going to do is, we talked last podcast on how you actually draw these structures. Now we're going to figure out what they look like. What are their shapes? What are their bond angles between all of those different atoms? So your first step is always to draw the Lewis structure, and that's what we did before. Then you're going to count the number of electron domains. And an electron domain can either be a bond. So if you have a single bond, a double bond, a triple bond, any bond just counts as one electron domain. And your lone electron pairs, those dots, those also count as one electron domain. So when you're counting those up, you need to remember that even if you have a triple bond, it still only counts for one electron domain. And then you're going to use that table. You're going to look up how many are bonded, how many have lone electron domains, and you'll be able to determine the molecular geometry based on that table. So your table looks something like this. The total electron domains is your lone electron pairs and your bonded pairs all together. So that's total what you have, and then you divide it up into lone and shared in these two columns right here. The molecular geometry is listed, and then you have your bond angles also. So this is what your table should look like. All right, I have an abbreviated version of the table down here because we're not going to have to go past 4 electron domains for now, so I just cut off the rest. But the rest of it should look the same as what you have. The first one we have is carbon tetrachloride. So if we wanted to draw the Lewis structure, carbon has 4 valence electrons, chlorines have 7, and there's 4 of them. So that would get us up to 32 electrons. So I'm going to have my carbon and my chlorines. And then I'm going to make sure each of my chlorines has an octet. Carbon is already stable with 8 electrons around it because it has those 4 single bonds. Maybe I can get all these dots. Okay, so this is our structure. If I were to count up all the electrons, I'd get to 32, so I know this is the correct structure. Here's how you use your table. You're looking at the central atom. So when we're focusing on these, you look only at the central atom. So in this case, that'll be the carbon. If I look at the carbon, there are 4 electron domains around it. This is 1, 2, 3, and 4. So for electron domains, I go to the 4s. It's going to be one of these 3. There are no lone pairs because there's no just double dots around the carbon. They're all single bonded. So there's 0 lone pairs. All 4 of them are shared. So that tells me that this is a tetrahedral shape and that the bond angle is 109.5 degrees. That means between each of these chlorines is 109.5 degrees. And you may look at this and think, well, that should be 90 because that's what it appears on your paper, but you're drawing it in 2D, and remember that these molecules exist in a 3D plane. I mean, in a 3D dimension, just like we do. So when you're trying to draw it on paper, it's hard to make it look 3-dimensional. It only looks 2-dimensional. So even though these appear to only be 90, they're really 109.5 because you have some going back, some coming out at you. And we'll build some models of these later on. Okay, our next one here is carbon dioxide, and we've already drawn carbon dioxide before, so I'm just going to sketch it really fast. This is what it ends up looking like. So again, we're going to focus only on the carbon when we're looking for the molecular geometry. And in this case, the carbon only has 1 domain here and 1 domain here. So it has a total of 2 electron domains. The only possibility is for it to be linear. So this is linear, and the bond angle is 180 degrees. So from here to here is 180. And the last one we're going to do together is ammonia, NH3. If I were to draw it, I won't count it out. It ends up looking like this. And we have to make sure that nitrogen has a full octet, so we put the lone pair up there. All right, in this case, we're going to focus on the nitrogen when we're looking for the molecular geometry. So nitrogen has 1, 2, 3, 4 electron domains. So again, it could be any of these three. It has 1 lone, and it has 3 that are shared, those bonded ones. So I look for the 1 lone, which is right here, 3 shared. It's trigonal pyramidal, and it has 109.5. Pyramidal. And what this molecule actually looks like is you'll have your lone pair on top, and the hydrogens actually are pushed down a bit, so it ends up looking like a pyramid if you think about it like that. What we need to realize is that when you have a lone electron pair, lone electrons take up more space than the bonded electrons. And that's a really important concept, and that's one we use that helps us figure out what these geometries are. So lone electrons take up more space than the bonded electrons. But that's all we're going to do for practice in this podcast. We'll do more practice in class, but just make sure that you're comfortable using that molecular geometries table.